Welcome everyone to Embedding Reasoning Routines. Reasoning, I believe, is a thread that goes through all of mathematics, helping children to sense make and understand and be analytical, whether they're performing written calculations or they're problem solving. I think it's interwoven throughout all of mathematics. We know that reasoning is also very predictive of long-term success in maths. Now, on the web page for this training session, I've put a little link to a research study that talks about how reasoning, fluency and spatial skills all predict long-term success in maths, but that reasoning is the most powerful of those predictors. But has mathematical reasoning become, to some extent, the preserve of the few? I want to look at how do we make sure that it becomes a normal behavior in a lesson for a child to reason mathematically, and how it can be something that's embedded throughout a school. So there's real consistency. When children come to a task, it's almost a default behavior that they would reason mathematically. How is it that we can do that? I want to have a look at how, by using similar structures for reasoning that children become used to engaging with, we can really then focus on the actual maths content of that task, rather than almost trying to explain a new technique too often. We also wanted to explore how children can think metacognitively, specifically in maths, and reflect on them as learners and what that looks like in a maths-specific context for children of different ages. And then how is it that children can be really creative in maths? I think children love having the opportunity to be unique and create unique discoveries. And I wanted to have a look at standard ways we can do that to open up mathematical tasks. Well, to start off with, what does it even mean to reason mathematically? What are these qualities? If we were to assess a child's attainment, we'd often do that based on what they can do in different specific aspects of maths, where they're at in multiplication, the kind of fractions questions they can answer. But if I was to ask you, well, what makes an outstanding mathematician? I don't think you'd refer to those skills. I think you'd refer to more general qualities. And my guess is, if we came up with a list of what those qualities were, they would be relatively similar. And I would call these the kind of reasoning habits that we're trying to build. So I'll share my list. You might add things, adapt things to that. But I think it might look something like this: that children are able to make logical leaps. So they can think, well, I know this, and with a bit of help, they can think, and therefore I can derive that. I can figure one from the other. A really important mathematical skill for us to develop for children. That, of course, they understand concepts. They're not just following procedures, but this is born out of a genuine, firm understanding. That children are flexible. They can see different approaches or perspectives. That's something we would aspire that children become in maths. Maybe that their thinking can be ordered, whether that's in the layout of the work or their approach to answering a specific question, finding different possibilities, say. That children are able to show their understanding in different ways. Now, that might be verbally, but it might be in other ways as well, with pictures, with equipment. And there's that, again, that flexibility and being able to represent thinking in different ways. That children are able to see relationships, patterns, make generalizations. This, of course, is the kind of the birthplace of algebraic thinking, if you like. So children not being overly focused just on if they found answers, but if they can see these patterns and relationships that exist within the mathematics. That children are able to be reflective, think about themselves as learners and how effective they're being, this kind of metacognition, and specifically how that applies in maths. That's something we would aspire for children to do. And also, and this I think is really important, as I'd mentioned before, the idea that children are able to be creative. And I think that would be a habit that I would hope to build within children. Now, what I would like you to do now is have a moment where you pause the video and just briefly, your thoughts on these things. First of all, what do you think to this list? Is there anything you would add or change? Again, reflecting on the children that you oversee, their relative strengths and weaknesses in each regard. Is there anything that you think you would like to build within them from this list? And what do you do to do that in your school context? So pause the video and have a think about that. So your thoughts on this list, what you'd add or change, your children, reflections on the children's relative strengths in that, and how you develop those skills. Okay, and then whenever you're ready, we'll play again. Now, hopefully that's been a good starting point for you to identify the things that you think are most relevant for you. You might think, I would like to develop children's ability to reason in this regard. And hopefully as we go through, you'll have the chance to think how you can make this specific to your children and your context as well. And we'll return to these qualities soon. Just first of all, though, I always like to start with this kind of basic image that shows this interrelationship between working memory and long-term memory. So the principle is that children are exposed to a stimulus, and they have a very limited working memory with which to process that information that's coming in. And that working memory can easily be overloaded. But we've got an enormous capacity for storing learning in long-term memory. And we've learned a lot about this interrelationship between working memory and long-term memory. For example, the importance of regular practice, retrieval practice, so that we can keep bringing those schemas from our long-term memory back into our working memory. We can strengthen them, send them back again. And of course, when we have those well-developed schemas, they lessen the burden on our working memory. Now, in planning for sequences of lessons, children will start relatively more novice, and then as we go along, will become more expert. And the first suggestion that I would give is the idea that different reasoning techniques will be appropriate at different phases of this journey. So earlier on, or where children are more novice, we might need to think more carefully about how children are able to reason within the limitations of their working memory, which could be easily overloaded when they have less expertise. But when we develop more expertise, there might be other reasoning techniques that we could introduce. They might be about combining different pieces of understanding from different aspects of maths, or comparing strategies, or creating children's own examples. They might be things that are inappropriate to do too early in a sequence of lessons, but become more appropriate. So as we go along, I'm going to introduce a range of strategies that I would use for mathematical reasoning. But of course, the skill of the teacher is to think, well, which strategy is appropriate at which moment in this phase of children's journey over the course of time. And that's something that I would really emphasize. Now, the other thing that I wanted to actually start with was more generic, so not entirely as math specific, but this idea that we know that working memory is really limited, but we want all of that limited capacity to be used up thinking about the maths in that specific lesson. So to start off with, I want to think about what is it that could eat into working memory, the capacity in working memory, and how can we make sure that as much of that space is used up as possible for mathematical thinking. So an example that you'd probably be familiar with: if a spider walks into the classroom, that takes a relative amount of a child's working memory up. Or maybe it's actually if they're hungry. That could be the thing that limits working memory. Now, they're two examples that you might not have much control over. But there are other things where I think we can create consistent generic habits that go from class to class to class, so have become embedded within children, that mean we're able to focus more of our limited attention on the actual maths in that lesson. Let me run through some examples. This isn't an exhaustive list. So I would encourage you, I'm going to share these examples that have been really relevant for me. At the end of it, you might think, I agree with this, I would add that, but you will experience other things that use up children's working memory, and think about how you could control them with really great systems. So let me share a few examples. The first one was from Kieran Mackle's book, and it was Matt Swain's idea, so I can't take any credit for this. When we say, show me your whiteboard, I wonder how much of a child's working memory can be taken up by the process of holding up a whiteboard that stops them actually thinking about the mathematics. It might be they're consumed by, has Mr. Metcalfe seen my whiteboard? Or having a look at what someone else has done, or it's been waved around and someone else is waving their board around, and they shouldn't be able to do that because now they can't see mine. So if all children are embedded just with this system of, when we say show me your whiteboard, the suggestion is held up to their chest, and that each child knows that they put their whiteboard down when their table is acknowledged by the teacher. So the teacher might point to the table on the teacher's right and go, And then all the children on that table put their whiteboard down and they know it's been seen. And the teacher moves to all the other tables. Now, that is just an example. If that routine is embedded in every class, then that's something that becomes habitual for children. And it means they don't have to think about that their limited working memory isn't taken up by thinking about, has the teacher seen my whiteboard? A few other examples, triggers for silence. Is it that we have to introduce a new one at the beginning of every school year? And how much, again, attention and time it can be used up? Could that be something that just becomes habitual, that children are trained into specific triggers for silence? One that I found very interesting when I visited a school recently was the language that is used to draw the children's attention back if someone's getting distracted. I've often heard the phrase "eyes on me" used, and then I heard a teacher using the phrase "track the speaker." So when a child's attention had been taken away from him, in this instance as the teacher, he said, "Remember to track the speaker." And this child was very conditioned to that, meant he needed to come back. And it wasn't actually placing the emphasis on the teacher, but on the speaker, which I thought really valued everyone in the community. Now, again, that was something that I really liked. And because it was something that was embedded and he'd heard consistently, it was almost an automatic reaction that he then came back together. In discussions, Doug Lemoff, in his book, Teach Like a Champion, talks about how we want to go really deep in discussions. And my suggestion of the way of doing that, to go really deep, is to have fewer participants. So to be interrogating fewer children in more depth. But how do we do that so that everyone is involved and actively thinking? Now, I know so many children in my lessons will have been sat there thinking, I'm going to wait and I'm going to put my hand up, and I'm not really thinking about anything until other than the thing that I want to say. And now I would routinely have the habit of asking children to restate what someone else thinks. And so in that way, I can ask fewer children to respond, but I can ensure that everyone is actively listening, because they know they might have to restate someone else's opinion. A way of making sure conversations are inclusive and deep, and that we're managing children's thinking. We're ensuring that the thinking is the key thing, that their thinking is focused on the key aspects of learning. We know, I know this from my own children, that so much of children's thinking can be taken up from fairness and motivation. And this might be tied into a reward system. So is it that I'm thinking, I will get a specific reward if I do this well? Is that the motivation? Is there consistency there? Because we know that that could well take up a lot of children's working memory. And again, having systems that are in place that are embedded throughout classrooms, I think, is really important for that we all have this consistent understanding of our approach there. We know that equipment is really important for building mathematical understanding, showing structures. And I, as many people, have always advocated using equipment. We know also that when we introduce a new representation, that can come with its own cognitive load. And you might know as well from just actually the practicality of children having equipment as well. And thinking about, where does equipment add value? In what form do I share that? And being aware of how many different representations is it appropriate then to use. Now, this is a huge topic that's perhaps something for, that there could be a whole another training video on, but certainly something to establish and something that there is consistency within a school on. Systems for recording. Do children know? I've seen lots of times where I've seen fantastic activities, but a lot of the children's thinking is actually, where do I write my answer down? Or, is there always consistency in how that work is delivered? Or does a lot of children's thinking come down with, well, which space am I supposed to write that down in? And how clearly is that modeled for children, for example? And the final thing is this. I used to be horrified at the idea that someone would come into one of my lessons and all the children are silent. I would always hold as a value that there's rich, engaging discussions, and I still hold to that. The only thing that I would add to that now is I've learned the value of short periods of silence. Children find it harder to block out background noise than adults. And also, if conversation is always there to be had, I actually don't have the same motivation to become independent. And if I know that I have to work silently for a short period and I have to become independent, it almost helps me to see my own capability as a learner. And so, again, having this consistency in the expectation that perhaps changes over the course of children's time as they go through school, of do we have periods of silence mixed in with discussion? How long might they be? And can we have consistency here? Now, you could argue over, is this taking away teachers' autonomy? Or can we have autonomy within this structure still? But meaning that we really build these habits within children with a focus on protecting working memory. Again, if you'd like to pause the video there, your thoughts on that, other things that you think would be relevant for protecting working memory, have a moment there to pause the video. And if you're ready, play the video again. Well, I always remember Emma Turner, who co-hosts a podcast called Mind the Gap, saying that systems always beat personality when it comes to improving children's learning behaviours, and that's always a principle that I really stuck by. And again, I just hope that you reflect on these things and think, well, how can having consistency here protect children's working memory, and also just to have this ongoing thought process of, is there anything that we can do to have greater consistency in this aspect of children's experience, in responses that we give, so children become habitually into these great learning behaviours, and for there to be consistency and agreed approach that's specific to your context. Anyway, what I wanted to do now is move on to the math specific content of what that looks like. And we were saying before that actually these are the characteristics that we want to develop in children, these reasoning, embedding these reasoning behaviours. Well, how do we do that? I want to be really explicit about how I believe this actually happens. So if we have these as characteristics, my suggestion is that if we use these similar techniques and approaches with consistency throughout the school, obviously progressively introducing these ideas through from year 1 to year 6, we develop habits of reasoning that will be enormously beneficial to children moving forwards. So when we go through, we'll look at each in turn. Now, if you have a look at the blue statements, they are the specific question types that I would use so to help children to make logical leaps, or to understand concepts, or to become flexible and ordered, and so on. And we'll actually look at them with examples, so I'll not talk about those ones now. The green examples are more things that will be interwoven right throughout children's experiences, and we'll see using the question types here how that's achieved. So, for example, being able to show understanding in different ways. The use of different representations, of course, is key to that. And through the examples, I'll try and share how that can be done, what that looks like. At the end, we'll get to how it is that we help children to be reflective by being really explicit about these learning behaviours that are context specific for maths. So we'll get there. And then in being creative, we'll also see through how using all these different question types, we can provide opportunities for children to be creative at different phases of the learning experience by creating, for example, their own versions of questions or extending thinking in every one of these blue contexts. So let's dig in and have a look what they look like. The other thing that I want to emphasize is this idea of, again, considering where are we in this sequence of learning, in this progression from novice to expert, and at which phase do we introduce which technique. The first thing that I wanted to get to is the importance of children being able to explain other perspectives. I talked about restating someone else's opinion. Now, a grounding for this could be, let's say if I flash up those dots on the left-hand side and take them away, and then ask children, well, what did you see? And if I ask adults that, they often say, well, I saw 4 and 2, or I saw 3 and 3. Children will often say, I saw an arrow, or I saw a giraffe, say, or I saw a frying pan. And so let's say if they say, oh, I saw let's say John says, I saw a giraffe. Because that's interesting. So which parts does John see there? Oh, so John, do you think John sees those two as the neck and those two as the feet? Whereas you didn't see, you saw, so Amy saw an arrow. So how did Amy see an arrow? And we need to consider that different perspective. Or very literally looking at the picture on the right-hand side and saying, what does the farmer see? What does the dog see? What does the cat see? Being able to see things from different perspectives. Let's say we've hidden Spider-Man somewhere in the classroom, and we could say Spider-Man can see two trees. He can see a road in the distance and a red ball. Where's Spider-Man? But helping children to see other perspectives, as well as helping to restate other opinions. Now, that is a really important grounding for the first technique that I wanted to have a look at, which is actually about understanding concepts through the use of misconceptions. Now, I've got a very specific route that I'll share for how I try and do that, using explain the mistakes and which answer. So these are techniques that I use generally fairly early in a learning episode. First of all, trying to actually build children's understanding before they have a misconception, and then getting children to be able to explain the mistakes. And I often start with explain the mistakes, being explicit that this is incorrect, and we will explain why it's incorrect. And again, I often do that with written calculation, like the example on the left. They're in the IC Reasoning ebooks, but they can also be created. Just looking at the most common wrong answers and children being able to explain the specific mistakes that are being made. It could be looking at a counting process here for younger children, introducing this idea of explaining the mistakes, that when we count on from 5, we don't actually count the 5. Or again, I might then move to which answer. Now, I generally want children to be confident enough to choose the correct answer before I introduce the technique, which answer, because it's better to be able to do that and then be able to explain the mistake than it is to introduce that as a misconception and that be a belief that children have. Early in knowledge acquisition, I want children to start having high success. So let me dig into very specifically how I might introduce misconceptions and build understanding prior to that. An example could be if we're looking to read the time from clocks. And what I want to emphasize here is the importance of children having expectations. So I might say, I'm going to show you 1 o'clock, and the first hand you'll see is the hour hand and then the minute hand. So where do you think the hour hand will be? And for children to form an expectation. The benefit of having an expectation is twofold. Either it confirms my expectation, so I was correct, and so that kind of strengthens the retention of that. Or I have a surprise. And if I have a surprise, I think, oh, that's interesting. And I attend to why it's incorrect, which is why I don't show the hands before the time. And then we see the hour hand pointing at the 1. And then where do we expect the minute hand to point to? And we see it's actually pointing at the 12. And then we compare that to 12:05. So where do you expect the hour hand to be? And where do you expect the minute hand to be? And we might say, how do we know it will be the hour hand? How do we know it will be the minute hand? And we notice that the hour hand is almost exactly at 12. And the minute hand, and now I might say thumbs up if you think it will be pointing at the 1, or thumbs up if you think it will be pointing at the 5. And directly addressing that likely misconception. And then again, children see and explain why the minute hand is pointing to the 1 lot of 5 minutes. And again, if I'm looking at 9:10, I might say, right, I'm going to show you where the hour hand goes first, and then the minute hand. Where do you expect the hour hand to be? And then we see it's just past 9 o'clock. And the minute hand, and again, we have this likely that children will think either the minute hand will be pointing to the 2 or the 10. And then again, we have this dual benefit. Either it confirms what children thought, or they have this surprise. 1:50. This time I'm going to show you the minute hand first. There's the minute hand. Where do you expect the hour hand to be pointing? And again, we get this idea that actually the hour hand is pointing almost at the 2, because it is almost 2 o'clock, but the hour hand is between the 1 and the 2, really focusing children's thinking on those key aspects. So when we get to the explain the mistakes examples, I want children to have, early in a learning episode, high success. Let me just give you a moment to have a look at those examples of the most likely mistakes there. And again, when children are explaining those mistakes, hopefully then they have high success. Now, the way that I tend to pair up those activities, often people will say to me, what about recording? And what does this look like in books? And what do you do with a whole class? Well, that's what I wanted to dig into next. Now, again, let's say I was looking at an example with fractions. I might think, well, what are the likely misconceptions when we're looking at the fraction of a shape? And I might bring up these examples and say, which fractions represent a half? And of the two fractions, is it neither, is it both, or is it one of them? And then we'll explain why actually it is the example on the right because we've got two equal halves, but it isn't on the left because there are three parts. And the possible misconception is we think there's one part that's blue and there's two parts that are white, and actually the denominator represents the number of equal parts. And then we have a look at another example, and again unpicking the fact that they have to be equal parts, so it's not just the number of parts. And then again I might get to an example like this one here and say which images show a half, and we can see that actually it is both, because if we look at the shaded sections, two of those parts would fit into the whole. So when we get to children explaining the mistakes, again, I want them to be able to have high success. Now, this is generally something that I do as a verbal activity with, it's not something that I look to record just because of the inefficiency of recording that. Now, if I wanted children to work independently, I'm more likely to introduce correct or incorrect, or a which answer. And in doing so, children can show which they think is correct or incorrect, and then potentially be able to explain for some of the examples why it's correct or the possible mistake. So again, if I just give you a few seconds to have a look at the example here. Okay, and let's have a look at another example. So let's say I was introducing Roman numerals. We might have a look at the symbols and their meanings, and then I could show that 20 is represented by XX, and I could say, I'm going to show you now 21, 22, and 23. What do you expect? And then we could see that each time we add an I, and say, I'm going to show you 25 now. And again, I might ask for an expectation here. And we see that it's two X's and a V. And then we'll discuss, what do you notice about this key aspect I want to draw attention to about 24? What's the same or what's different, or what do you notice there? And draw children's attention to the fact here we have an I there, at 1 as subtracting from the 5. So then when we come to the explain the mistakes example, again, hopefully children have relatively high success. And again, I might then ask children independently to work on a which answer example, where they select the correct example, and then verbally, generally, I would hope that they would be able to explain the possible mistake. And again, if I just give you a moment to have a look at those examples, and feel free if I go too quickly to pause the video. So again, hopefully you can see how this is a generic technique that can be applied across the age range and can really emphasize that mathematical reasoning. Let's have a look at another example. And one thing that we'll often do is use bar models to highlight specific differences between correct and incorrect, and really highlight, if you like, the variation between a possible misconception and a correct answer. So in a moment, I'll ask you to pause the video and have a look at this example. And children are asked to explain the mistake and then do the correction. So again, if you could have a think about how the correct image will be different to the mistake that's shown. So pause the video and have a think about that one. Okay, and whenever you're ready, let's play again and let's have a look. And of course, the key thing here is the ratio is drawn in the same way for both examples, 3 children for every 1 adult. And of course, the difference is there are 12 more children than adults on the trip. So the 12 is actually represented by those 2 parts, not the 3 parts. and then I can model how the then the effect. But it's focusing children's attention on those key differences. Now, another really big topic, of course, is the use of representations. Now, again, I'd said before that this is something that I would interweave generally early on in a phase of learning to represent structures. Now, again, this is a huge topic, and again could be its own training episode. But what I just wanted to emphasize are these big ideas when we're showing understanding in different ways, which is we want to show the underlying structure of the maths. When we use equipment, it introduces extra cognitive load, but they have enormous value. And I guess that my encouragement would be to think about how many structures do we use, and not introducing too many, but just enough that we accurately represent the mathematics. And how do we consistently use that equipment so that children are used to using each piece of equipment, and they have clear guidance and form clear habits about how equipment is used specifically, again, to manage cognitive load. I've also just thrown up 3 examples from the IC Reasoning ebooks, which I think are nice visuals, which again can be brought to life practically, but I think are nice visuals for representing specific concepts. So again, at that point, I'm just going to ask you to pause the video and have a think generally about that consistency in the use of representations. So again, if you pause the video there. Okay, and in moving on from the use of representations, I want to get to one of my very favourite techniques once children are fluent in calculating, say, to introduce reasoning. And it's really important that we get children's learning behaviours really built to access these questions really well. And the techniques that I wanted to look at are I know and so, and small difference questions. I like to think a great combination, any great double act like Batman and Robin, Morecambe and Wise. We have I know so and small difference questions. The key thing is getting children to make logical leaps and see, well, I know this and therefore I can derive that, this very essence of what it is to be a mathematician, and to be able to see relationships and generalize. It's enormously powerful. And actually, I find an amazing tool for differentiation because there are so many things that can be drawn out from these examples. I tend to introduce with an I know so, particularly if I'm modeling with a class, and then move on to small difference questions with the children. Now, again, all the examples here are from my IC Reasoning ebooks in these examples that we'll look through. But again, I would encourage you to think about how you can apply these generic techniques with the resources that you use or create as well. So the philosophy behind I know and so, first of all, is noting, well, what about the question to the one before is the same and what's different? And therefore, what do I expect to see about the answer, and being able to relate them rather than seeing them separately. And I try and be very explicit in the I know and so examples about the relationships between the questions. That's the skill that we want to develop with children, where they notice what's the same and what's different about the question, and that becomes a routine. They predict what do they think that will result in. They check that outcome, was it what they expected? And then they explain those relationships. And again, I'll be looking at entering here when children are fluent enough within the calculation that they're being asked to perform, so that they can then explain those relationships. So again, it's about introducing at the right point, or possibly just knocking down the level of challenge in the calculation so that we can focus on that challenge in the reasoning. Let's have a look at this context here. 32 divided by 8 equals 4. 38 divided by 8. Well, what's the same and what's different about the question? Well, we've got the same divisor, and the dividend, what's different? The dividend has increased by 6. So what do we expect? And again, with the question below, 30 divided by 4 is equals 7 remainder 2. 38 divided by 4, what's the same and what's different? And for children to make expectations, even if they can't make an expectation when we see the answer, I might say, what do you notice? What's the same and what's different about the answer? Let's say we're looking at 30 divided by 4 equals 7 remainder 2. And I might say, well, what's different is that the dividend increases by 8 and the divisor is 4. And what do you see about the answer? Well, what's the same as the remainder, but what's different is that it's 7 remainder 2 becomes 9 remainder 2. It's 2 more lots of 4. And being really explicit about those relationships and explaining those relationships. And again, we could have a look at then the next few examples. So let's say we could look at 50 divided by 6 equals 8 remainder 2. So what do you notice that's the same and different about the following question? What's your expectation? And children making expectations. And if they can't make that expectation, if we calculate the answer, can they explain the difference that we see there? And again, that could be modeled with the examples on the right-hand side. Let's say 24 divided by 3 equals 8. 48 divided by 6. Well, I can see that the dividend and the divisor is doubled. And often we'll have the misconception, then the quotient will double also. Or maybe not, and maybe we think it will stay the same, and we can explore that as a relationship. The I know and so questions, I tend to use as a precursor to the small difference questions. If I bring up this example here of a sequence of small difference questions, and just give you a moment to have a look at that sequence. Now, again here, a child might be able to calculate the answers and see them all separately. But we have this great possibility for reasoning if we put the questions in an order where the differences between each question is small, and we ask children to look for and explain those relationships. For example, 14 divided by 4 equals 3 remainder 2. So 28 divided by 4. Remember saying to this child, I think that the answer should be 6 remainder 4. And she, after some thought, figured, well, actually, you can't have a remainder of 4 when the divisor is 4. And let's say for the last example, she'd calculated the missing dividend divided by 8 equals 4 remainder 6. Well, I have to do 8 multiplied by 4 and then add the 6 to quite some thought. We calculated the answer of 38, and only then are we able to see, well, what's the same about those questions? That the divisor is the same, and for the quotient we've got 4, but the remainder it changes by 4, and therefore the dividend increases by 4, and we have this, okay. And now she accesses that next sequence differently. Now, there's so much scope for extending and explaining the relationships, or even can children create their own examples to continue those sequences and be creative in that way? Which examples, what would the next 2 questions be that they would add in? What are they demonstrating there? Can they change just one thing or 2 things to keep something the same? So enormous possibility. And again, the I know so questions help me to access this really well as a precursor. So again, I use the same technique with younger children, so long as they are able to access the calculation. So if I could just give you a moment to look at this example. And again, if I just quickly draw out one aspect here, the child knew double 6 is 12. And then the child knew 7 add 5 is 12 because I put 7 here and then the 5, and I could see her visualizing how the 5, I take 3 to make a 10, and then there's 2, so it's 12. And then we look, that's interesting, the answers are the same. Why are the answers the same? And then she realizes, actually, essentially double 6 is the same as 7 add 5. I could take 1 from this 6 and move it to, and that becomes a 7 and that becomes a 5, and the answer's the same. And we have the potential to see that relationship because of the sequencing of the questions. An amazing technique, I find, for opening up the possibility of reasoning whilst practicing calculation. So again, another kind of Batman and Robin combination, if you like. I know and so, being very explicit about explaining the relationships that exist, and looking at, well, what's the same and what's different about the question. Or maybe I state what's the same and different about the question, and I say, so what do you expect to be the same or different about the answer? And for children to be able to articulate that very clearly. And that enabling children to have success when they come to accessing the small difference questions beyond just calculating the answers. And again, I would look at having a clear or a shared expectation of how children then explain those relationships. Is that just verbal? Do we look at drawing out one example that we'll draw children's attention to that we want them to explain? So if I draw your attention to the middle sequence here, we have 2 multiplied by 8 is 16, child just knew the times table fact, and for 4 multiplied by 8 is 32. And then we were looking, well, so double 16 is 32, but we don't continue the doubling sequence, because actually 6 times 8 is 2 times 8 plus 4 times 8. Can you see the markings there? She was able to explain that relationship. And then again, she works out 12 multiplied by 4 using just a separate calculation strategy. And we see the answers the same. And when we see the answers the same, it draws our attention to, well, why is that? And we're actually looking at that doubling and halving strategy. Double 6 is 12, half of 8 equals 4, and therefore the product is unchanged. And again, children could then create their own sequence to demonstrate their understanding and really be creative there. Let me have a look at how I might model the precursor to using a sequence of questions about negative numbers in upper key stage 2. So here I might show this sequence. It might be that I have a number line to represent that as well. And we see and ask children to comment on the sequence, or what do they notice, look at the differences between the numbers, and then bring up another one and say, have a look at this. What's the same and what's different? And again, I'll throw in a third example. Okay, and so what do you notice here? What's the same and what's different about the numbers in the sequence? And we might look at the differences between the numbers in the sequence and where we start from and so on, and model that. And let's say I'm going to take these same examples and say, okay, so these are the same sequences you've just seen, and then ask children to model, well, how would we continue this sequence? And to recognize, well, what we'd do is we'd look at the difference between the numbers in the sequence, and then we would continue, in this case, adding steps of 2. What about the next example? And I'm deliberately using an example that they've actually already seen, because I want the children to have higher success. Well, here I need to work out the difference between the numbers in the sequence, but what's different than the example above? Well, here, if we have a look, that's a jump of 8, but it's actually in between the 2 jumps, if you like, in this. So to work out what each interval is, I have to halve that difference of 8, which is 4. And then again, I can fill in the gaps. And with this last example here, I can say again, from this case, what's the same, what's different? And here, of course, the difference is we have the same gap that we had previously, but now it's 1 negative number and 1 positive number. And so there we have a difference of 12 to halve. So again, that I'll be very explicit about. And with the aim that when children get here, they have relatively high success. Now, again, my recommendation is, rather than just saying to children, right, off you go, first of all, could they articulate, well, have a look at the sequences, and before they get their pencil, can they say, well, have a look, what's the same and what's different about from example to example? And we develop that skill first of all. And if I was looking for children to make a prediction, what I could say is, which sequence will have the largest 5th value? What do you expect? Now, we're going to have a benefit in making that expectation, either if that expectation is correct or incorrect. So if I just give you a moment to have a think, what would you expect to have, which sequence to have the largest 5th value? And again, feel free to pause the video if you want slightly longer. And then again, of course, we could model the process of looking at, it's just if you're curious, the difference between -5 and 7 is 12. And so using that as the intervals, well, what's the same and different about the next example? Well, that difference is still 12, but this time it's 12 for 2 jumps. It's a gap of 6 and so on and so forth. And then again, we could look at this next example where, again, we still have this same interval of 12, but this time it's split between 3 different jumps. And how that changes the intervals, and then again this last example where now we have a negative number and a positive number. It's just that difference has changed, so this time it's 18 divided into 3 sections. And then again we could look at that prediction. Was your prediction correct? Could children then add another example? What would their example be if they were to create their own example? Why would they choose that? So what difference would they create from that last question? Often asking, and this is from Craig Barton's book on this subject, could children come up with 2 other examples to extend that sequence? Again, on the subject of children creating their own examples in being creative. So the small difference questions on the left-hand side, again, are looking at this, looking at these little variations and how does that affect which, have I got a part or have I got a whole? And then asking children, well, can you now create your own sequence of questions? And I might point to the fact that, do you notice that of the numbers that are provided in the question, that the smaller number is always a factor of the larger number? Why is that? And then again, children creating their own sequence and really embedding their understanding in doing so, but also having this important opportunity to be unique. And again, just to demonstrate that this technique I use with younger children as well. So let's say if I was looking at the right-hand sequence there, and I was modeling, and again, children may just, first of all, then first step might be they've just calculated the answers. And what we do when children have the comfort of having the answers is model, well, what do we notice? So 10 subtract 7, the difference between 10 and 7 is 3. So have a look at the next question. Well, what changes is 10 there, that we are subtracting 1 from the minuend and the subtrahend. And what happens to the difference? Look, it stays the same. It's still 3. Well, let's have a look at the next question, 8 subtract 5. What changes? Well, the 9 becomes an 8 and the 6 becomes a 5. And what do we notice about that difference? It's still 3. And really drawing out those relationships. I want you to have a think about the following things. So finding or creating the sequences of questions. Where could you get the sequences of questions from? What do you use currently to do that? Could you create them? How will that work best in your context? How could this be introduced in different year groups? So what would the expectation be that would be appropriate for your context of which skills we will explicitly teach to build these habitual behaviors? Because we want to really value that process of explaining those relationships. So how is that phased? How is it first introduced? How is the expectation develop and look different in terms of the recording, say, as well? And how is it that we actually model the teaching of children spotting similarities and differences, making predictions, explaining relationships, and modeling what it looks like for children to effectively create their own examples? How could this look in your context? Pause the video and have a think about those things. Okay, and if you're ready, let's continue on. Again, my encouragement would be around the small difference questions is really thinking about how do we build those routine behaviors, so when children see those questions, they automatically think about, well, what are those relationships and how can I explain them? And that is, of course, a process that needs building, but not just by one person, by the whole team. That, I think, is where you get the absolute benefit. So hopefully some food for thought around the importance there of consistency for building those habits, those reasoning habits that we really want to get children in. We'll move on now to have a look at some of the other techniques that I would generally look at introducing. If we want to make children flexible, I tend to look for different method questions and rank by difficulty questions. So different methods questions are questions that lend themselves to multiple calculation strategies, and they may often have a visual attached to them. So for example, 39 plus 38, children will often go for a standard column method, which is actually, when it's seen with a visual, might be perceived as being more difficult. So it's like doubling 30 and then having to add the 9 and the 8. As opposed to when we see the image, we're more likely to think, well, it's 2 lots of 40 if I subtract 3. Or to think about, actually, if I move just one of the red counters, which of course could do it practically, one of the red dots in this instance, and to complete a 40, then I can see it's 40 add 37. And again, different ways calculation, like 25 multiplied by 18, a calculation that lends itself to multiple possible strategies, like doubling and halving, it's equivalent to 50 multiplied by 9. To think how much less is it than 25 multiplied by 20? It will be 2 lots of 25 less. Or seeing the 25 as 5 times 5, as breaking down into the factors, or indeed as 100 divided by 4. So questions that lend themselves to multiple strategies and really kind of embracing that. Here's some examples again that would be fitting for younger children with the matching visual. So if I just give you a moment to look at those examples there. And again, it might be that we provide a question using the visual representation and look for different strategies, and then perhaps have another one that using the related strategies but without the visual representation, and see if children can use the kind of mental imaging to be able to calculate in different ways. And again, this is a favorite, an old favorite one of mine, where a child was asked to do 12 times 7 in 3 different ways. And she came up with a bronze, silver, and a gold strategy of different ways I could manipulate. I could break down the 12 into 11 and 1, the bronze method, or the silver method, actually partitioning the 7 instead of the 12 into a 5 and a 2, or even just doubling 6 sevens. And that was built on examples like this, where we're looking at the different ways we could partition 14 multiplied by 6, or just saying to children, giving them a grid. Theirs don't look as neat as this. Giving them a grid with a 14 by 6 grid and saying how many squares. How can you work it out without counting all the squares? How can we break that down? Maybe model some examples. We could split it into the 14 into a 10 and a 4 multiplied by 6. Or maybe we actually split the 6 up into 3 sections of 2. Or again, maybe we halve the 14 rather than splitting it into a 10 and a 4. So we can see 7 multiplied by 6. But again, encouraging those different calculation strategies where appropriate. Now, in flexibility, one of my favorite techniques, which I tend to introduce in Key Stage 2, is rank by difficulty. Now, of course, children would need the different calculation strategies to engage with rank by difficulty. But the idea is it encourages children to use different strategies, or to think about what makes a question relatively harder or easier. Now, the children, you might give children 4 questions and they'll answer them anyway. And rank by difficulty, they're able to analyze the different possible approaches. So again, can I just give you a moment, and feel free to pause the video, but just to have a look at possible strategies for these 4 questions here. Okay, so do children recognize that actually to work out 64% of 100, that is just 64? Or do they start working out 10% and 5% and so on? And similarly, 99% of 300. Do I just actually recognize that is 3 multiplied by 99 and so on, and see different possible strategies? Whereas 30% of 400, perhaps I work out 10% and I multiply by 3 and look at the different possible strategies that could be used for those questions. Now, again, here's another pair of rank by difficulty questions here. I really like these ones because, again, they really pull out the different mental or calculation strategies that could be used. So again, here, if you just pause the video and have a think for these examples of the different strategies that the questions lend themselves to children seeing. Okay, and whenever you're ready, if you play again. So it might be that for the division examples, we could look at, we might consider 27 divided by 9 easier because 9 is a factor of 27, as opposed to 38 divided by 4. Or perhaps if we're looking at 100 divided by 4, we see we move from to a sharing strategy, potentially halving and halving again, rather than thinking how many 4s in 100 and getting children to articulate that. And where we're looking at how many 3s in 40, it's more than 10 lots of 3, and maybe children then consider that more difficult, and so on. And again, the bottom examples, it might be that automatically children think that the numbers with more digits will be more difficult. But if we're looking, for example, at 4050 plus 602, we can actually just add the numbers in the individual columns without any, because we're only adding zeros in the 1s, 10s, 100s column. And again, we can look at calculations like 97 plus 126, we might consider that more difficult if we're doing a column method. Whereas we might see, actually, I could just adjust with compensation strategy to 600 plus 123. So again, questions that really encourage those different methods. Maybe seeing that 83 and 17 are a bond to 100, and then just adding the two other 100s for the top left example there. But really like rank by difficulty, only when children have the expertise of actually seeing the different strategies. So again, later generally in a sequence of lessons, and children being able to explain those differences. If you have a look at this small difference questions here, this one also lends itself to children thinking, well, which questions are more difficult, which are easier, and why is that in these instances, and looking at the challenge actually in bordering tens and hundreds in specific instances. So again, if I just give you a moment to look at this example. And maybe, for example, helping children to reflect on the difference between calculating, in calculating 107 subtract 100 and 107 subtract 10. And again, those small differences really emphasize that little change. If we, and again, in terms of creating questions, I find that children are fabulous at designing their own rank by difficulty questions and thinking then about the different strategies that they lend themselves to. This was an example that actually from the home learning lessons that I put together, which has always stuck with me, of a child. I actually didn't see this strategy at first, for 25 multiplied by 24. And then she explained, actually what I would do is just double and halve twice. So it's equivalent to 50 multiplied by 12 and 100 multiplied by 6. So again, questions that lend themselves, some that lend themselves to alternative strategies, and children creating their own examples is a wonderful way of them kind of expressing that understanding. One of the final techniques that I wanted to introduce was how many ways questions, for getting children to really order the thinking, and also to be able to access challenge for many children, being able to find an answer, but there being the built-in challenge of either I can find different answers, or I can find ways of working systematically to know how many answers there are in total. So again, if I could give you a moment here just to pause the video and just to have a think, how is it different? And perhaps have a go at one or maybe both of those examples. How is it different finding an answer to finding different answers, to having to work in such a way as I know I'm going to find all the possible answers? And what will we model? How will we model that as an approach? So again, if you can pause the video there. And whenever you're ready, if you play again. I'm often asked, are there answers in the ebooks, which of course there are. So having a look at the top right example, so fill in each gap with a single digit number. So perhaps I could recognize that it can't be half of 24 because that's 12, and then I don't have a single digit number in that box. So I might come up with an answer like a third of 24 equals 8. And then it might be I start to search, right, well, I found a third. Well, perhaps it could be a quarter, and then I might get to, it could be an eighth as well. An eighth of 24 equals 3. And from there, it could be, I see that 3/8 is 9, but how do I find a system? What could my system be then for knowing that I found all the possible answers? And again, how could I model that systematically to ensure I know I found all the answers involving a quarter, all the answers involving, and so on. And again, I like the bottom left example in, first of all, recognizing that it has to be the missing digit there has to be in the subject head has to be a 7. To subtract 7, it must involve a regroup. So it must 12 subtract 7 equals 5, and then working systematically to work out the combination of values. And of course, it must be a combination here if there's 2 missing values. So there are different possible answers. And then, so I could look at 9 subtract 3, and then work systematically down, of course, finding all the different answers. 8 subtract 3, and then 7 and 3, 6 and 2, 5 and 1, and of course then we finish with a pair of 4 and 0. Now again, the idea of extending in this instance is thinking, how could I change one of those digits in the given question to create 2 more possible answers? And specifically looking at the 3, and thinking in the subtrahend and thinking in the tens column, and how could I adjust that to create more possible answers? So a brilliant way again of a task that many children could be able to find an answer, but being able to find all of the answers, knowing how I know, and then being able to extend, hopefully is a task that many children can access, but there's enormous scope for depth there as well. Now, other examples, just to make the point that the how many ways tasks span right across the curriculum and right across the age range as well. They might manifest differently for younger children. I might look for different ways examples. So if I just give you a moment to look at these examples, think about what we might draw out about the make 20p question, and give you a moment to think about those two. Okay, so again, with the cubes, I could find an answer, but knowing systematically that I found all the possible answers is a wonderful way of exploring there. And again, with the 20p question, I would draw out the specific changes. For example, from 2 coins to 3 coins, what stayed the same? What was different in finding my next answer? And then from going from 3 coins to 4 coins. And then again, it could be that we draw out why I can't keep 3 of the 5p's when I'm going from 4 coins to 5 coins, because I can't split a 5p into a 2 and a 3 or a 1 and a 4. So much reasoning that can be drawn out there. Now, what I wanted to get to with this idea of metacognition and helping children to reflect on themselves in a way that's specific to maths. This is something that I use to help children to self-reflect in year 6, although I would focus on specific elements and model what that looks like. And what I would ask you to think about is how we could work backwards. If these are the qualities that we want children to have eventually, how is it that we will drip feed and model what it is to reflect and how we celebrate these characteristics as children go right throughout the school? I say that that I want children to start working by themselves rather than starting with a partner, because when they do, I believe they're more likely to have more to discuss, and it won't be one person leads and the other person follows as much. Then they can have a discussion. That we want children, as discussed before, to be able to follow the thinking of others and see what they can restate other people's opinions and say what they agree and disagree with and see different perspectives. That children have the ability to check their own success, which I think comes down to them also having periods where they work independently as well, and seeing what they can do well and where they need to have more help specifically. That again, children can show their understanding in different ways, and that they are independently able to extend their own thinking. I've had children before further up the school analysing their relative strengths in these aspects and setting themselves a personal target. Now, where children are younger, it would more be, we would perhaps first just be modelling one element of this and what that looks like at a time that is appropriate. So again, what I wanted you to help you to think about now and give you some time to think about is how do we build up to children being able to have these skills, and how do you see, could you see this working as a tool for self-reflection, and how could these skills be built throughout the ages? So again, if you pause the video and reflect there. Okay, and whenever you're ready, if you keep going again. But again, these I believe are key aspects that are specific to maths that will help children in their ability to reflect. The final thing I wanted to consider was about teacher responses and consistency again here. So children get consistent messages that are specific to maths going through their experience in the school, and just some food for thought. The first thing is responding to misunderstanding. I think there's value if children have made a mistake to try and think about, almost to be able to communicate to them that there's nothing wrong with their ability to learn. And one thing that I always encourage is to think about how I, as a teacher, might say, you know, I obviously need to do this differently, or I will think about how I can to communicate the idea that we believe that everyone can effectively learn. And it might be there's also, we communicate responsibility to the child. And so you can, and then, or next you're going to need to, to make sure that we have that consistent message at a point of misunderstanding or lack of success, of the agency that we all have to improve, that we all have that capacity. In responding to errors, where children make mistakes, if children have a misconception, we might consider this different. But if children make mistakes, it might be that we provide less specific feedback and ask children, let's say, 6 are correct, 2 are incorrect. And they then have more work to do to find where the mistakes are than if I tick and cross and ask them to make those corrections there. We want children to celebrate the process of learning. And again, I would ask you to think, what do we do where children make mistakes? Is it correct to celebrate those mistakes? Because I guess what we want also to be able to do is celebrate excellence and making that progress, but for children to feel comfortable in that as well. So again, I would just think, do we give consistent messages in that regard as children go throughout the school? I think it's a worthwhile discussion to have. This you might well disagree with, but I think it's really important to reflect the genuine emotional experience of maths. And I believe that what that is that there is discomfort that is a precursor to achievement in maths. When we as humans, when we have to learn, our brain actually releases a stress chemical, epinephrine, to make us be able to focus better, to prepare ourselves for learning. And so when we're going into a place of learning, there is, biologically speaking, a discomfort. And I believe that maths is enormously enriching. I don't describe maths as being fun. I describe maths as being an exciting challenge, because to me, it isn't fun, because learning comes with stress as well as that excitement. Maybe the fun comes later. But I believe it's really important that we don't missell what maths actually is, that we need to embrace that challenge. We need to walk through that difficulty, and that is actually, the joy is almost on the other side. And again, I think that it's important to accurately reflect children's genuine lived experience in mathematics, which biologically, I believe that reflects it well. And the final thing is doubt at the point of answer. I always encourage to think, when children give you an answer, if we respond indifferently, we force children to check that response and justify it. And they're things that I think we want children to do. We don't want to condition them into being happy just when they get the answer right, but we're looking for them to justify how they know. And doing that consistently throughout a school, I think will build that naturally within children. It'll just become habit forming. Again, if you can pause the video and your thoughts there. And again, whenever you're ready, then play the video again. Well, I hope this helps to give consistency for teachers, consistent messages. Let's have a look at what we've covered in this video so far. Just a recap: classroom habits that protect limited attention. So looking out, what is it that could use up children's working memory that otherwise could be, the space that otherwise could be used for mathematical thinking? How can we control that? Keep on having that thought around how that can be done. With misconceptions, how we use misconceptions, but also the power of prediction beforehand, and children thinking what they expect to happen, comparing that to what they actually see, as a lead-in then again to using misconceptions. Starting off by children being able to explain mistakes, or giving which answer examples which might lend more to children doing independently. How we emphasize relationships between questions, using techniques like I know so and small difference questions. I always like to use the same headings so that when children see small difference questions, it just triggers those behaviors. So again, the consistency within that might be something to consider. And then again, how is it we build depth in through comparing different possible strategies, creating children's own example questions right throughout all the strategies, and again being systematic to those how many ways questions. And then again, the overarching theme, I would say, of this video is the consistency with the teacher responses for the messages that we're giving about what it really means to be mathematical. I hope you found this really useful. Please stay in touch. Get in touch with me on social media, or my email, which is icmaths@hotmail.com. Have a fantastic school year.